Hello, welcome to Right Protection Enforcement. My name is Ahmed Abdulraouf. I'm a graduate student at Passau University, and this research was conducted as part of my graduation thesis at Alexandria University alongside with my professor Mohammad Azab and Igor Stoppa, who is a Linux kernel developer and principal engineer at Huawei. So, our goal here is to harden the operating system against kernel level rootkits with very little or no overhead. And by harden, I do not mean detecting rootkits, but rather making it super hard to insert a rootkit into a running operating system. And we want to have a clear boundaries between the policies that can be configured to guarantee protection and the mechanisms that executes the policy. Our system has a wide range of targets, ranging from cloud or virtualization based high performance computing down to a mobile phone that supports virtualization. In order to comprehend what our system achieves, one must first understand how cyber attacks work. Generally speaking, an attacker would first start by gathering information about the target and use that information to identify an attack surface or vector, and then they keep running in this circle until the attacker figures an exploitable surface. Once the attacker finds an exploitable surface, he would gain a full control over the system. Depending on where the exploit was found, the attacker may or may not need to escalate his privileges. For example, moving from a normal user to root user in Linux or gaining administrative privileges in Windows. But at the end, unless the attack was a hit and run style, the attacker would deploy post-exploitation techniques to maintain his stealthy access to the system. Usually they attempt to insert a rootkit into the system in order to maintain access while hiding all the tracks, including files stored in disk, network traffic, running processes, or even memory footprint. The hardest kind of rootkits are the one that targets the kernel itself. The reason is that most, if not all, of user space software depend on kernel to do their job. Now, if the kernel is lying about what's really going on or hiding something, there is virtually no way for a user space software to efficiently figure out what's going on. And that's where right protection enforcement is concerned. Our goal is to make this phase of attack almost impossible. For the purpose of this research, we assume that the attack has complete access to the system. The attacker can run any code they want with any privileges, including both running code as root or at kernel level, ring 0. But all the same, our goal is that they will never be able to hide the fact that they were undermining the kernel or hiding something. Right protection enforcement is composed of two layers. One is a kernel layer named PRMEM, and the other layer lies in the hypervisor and it's called ROE. The two layers coordinate with one another. The way this works is that PRMEM provides tool for the kernel developer to protect their code and data, while ROE makes this protection enforced by a hypervisor. And the way it works is that ROE makes sure that these protections are not only enforced but irrevocable until reboot. Primarily, the purpose of PRMEM is organizing data in pages according to various types of affinity such as scope, where the memory from the same kernel subsystem are placed together. Another type of affinity, and an actually important one, is protection, where memories that have the same protection are lumped together. PRMEM achieves that via linker script and custom attributes in case of static data, while for dynamically allocated data, PRMEM has its own pool-based memory allocator. Traditionally, the only available option when it came to protecting data was making it constant, and by constant I mean read-only, and that was very limited for obvious reasons, like who knows what the data was at initialization. But the kernel itself introduced a new type of protection named read-only after init, where data segment was marked as read-only after the kernel initialization is completed. PRMEM expands this concept by introducing write rare after init, where data that has been tagged with a specific attribute will become modifiable exclusively through a write operation that may be performed by hypervisor upon request. This slide shows how data is segregated by PRMEM within different address ranges based on its properties. Such segregations allow verifying protections of a given memory buffer based on some conditions like, does this memory buffer fall within one of the supported memory segments, or is the property, the accessing that's done on this memory buffer is compatible with the operations that are normally allowed within that segment. Such properties can be trusted to be correct as long as the hypervisor provides protection against double mapping, because remapping a physical page would be the only way for attacker to sidestep these verifications. The verification from kernel side is relatively inexpensive and actually very efficient. All it does is comparing one memory range against another to make sure that they are contained. To avoid attacks attempting to trigger use after free scenarios, PRMEM doesn't allow freeing memory. Memory is allocated through pools, and pools can only be released entirely, so you either deallocate the whole pool or just keep using the pool even if you need a single byte there. The pools are also a mechanism to implicitly indicate what are the properties of certain allocations. These properties are associated to the pool once it's created, such as, for example, it might be rewritable. When memory is allocated for a pool, it automatically inherits the property of the pool. When such allocation undergoes one of the previously mentioned operations, like any kind of access, it's verified accordingly by checking the ranges and such. In order to understand hypervisor component, one needs to fully comprehend second level address translation mechanism, and that is a mouthful name for a tool provided by CPUs to facilitate creation of fast virtual machines. For the rest of these slides, we will refer to the second level address translation mechanism as an EPT, which is short for extended page table, and that's how Intel refers to this technology. That's the non-vendor neutral naming. First, we will start with a simple schoolbook normal page table. Here we have the control register 3, which holds the base address of the page directory, and then the directory part of the linear address is just an offset to that page directory. The data stored there is the base address of the physical memory frame, and to access the data stored at the linear address, we would add the offset part of the linear address to the memory frame. Then we have the physical address, which is equivalent to the given linear address. It's just a basic how address translation happens. Normally, an operating system can customize the page table to its need by configuring read, write, execute permission for every page. In order to build EPT on top of our schoolbook paging, we will have two completely separate page tables, one that acts completely normal as per the guest kernel concern, but then the physical address that's produced from the linear address doesn't really exist. When the kernel tries to access the data stored there, the CPU realizes what's going on, and instead it checks other page table that's created by the hypervisor to convert the guest physical address space into real physical address space. The point here is that the guest cannot access the EPT table, and it's not even aware of its existence. EPT comes with the same features as normal page table. You can have permission management per page, except for that the one controlling these permissions are not the kernel, but rather the hypervisor. Now, in real world, we do not have the schoolbook paging, but instead, in Intel, they use hierarchical paging, which is just a fancy way of saying we will do the lookup 4 consecutive times instead of one. The design objectives are out of scope here, but we can say that they do it because page tables are better represented with a sparse tree rather than just one big array. And EPT is also hierarchical page table. Now I'm sure some of you can imagine how complex drawing or visualizing this would be, but being hierarchical or not, it's not an important details for the sake of presentation. The only difference it made is for implementing stuff. And from here on, I'd stick to the schoolbook EPT instead. ROE is composed of two separate parts, memory ROE and register ROE. Memory ROE is basically a communication channel between operating system and hypervisor, where operating system restricts its access to its own memory. The way this communication happens is via what we call a hypercall. One can think of a hypercall as a system call, except that this time kernel itself is requesting something from the hypervisor, where in system calls it was a user space program requesting something from the kernel. Once the hypervisor receives a request, it will make sure that such requests are always honored, even when the operating system decides to change its mind, such as in case of an attack. Memory ROE can provide protection for full memory frames, or it can be as fine-grained as needed down to protecting a single byte. Conceptually, memory ROE can be implemented via full emulation, where hypervisor would just emulate all data movement instruction and maintain a table of which bytes are protected and which are not, and for every move instruction it would check these bytes. A more efficient way is to use EPT to enforce the protection. In case of full ROE protection, it's simple. The page would just be marked as read-only, and the hypervisor would never allow any writing on this page to be done by the guest operating system. Partial ROE protection is a little bit more involved. In order to protect a single byte, the whole page will have to be marked as read-only by EPT, but that's not the end of it. The hypervisor would keep track of this page and which bytes of this page are read-only and which bytes are readable and writable. So when an operating system attempts to write at these pages, the CPU notes that it's protected, so it triggers an EPT fault, which is basically the CPU falling back to hypervisor to figure out what to do, in which case the hypervisor will check if these bytes are safe to write to or not. If they are safe, the hypervisor itself will emulate the writing operation. If it's not, it will just prevent the writing, or it's just part of the policy. It's up to the hypervisor to determine what needs to be done. It might be a little bit obvious that partial ROE has some overhead over full ROE, and some may say it might be completely unnecessary feature, but that's not true. While PRMEM may not need to directly allow users to use partial ROE, it's still needed to enforce protection when guest operating system supports paging. This diagram shows ROE in action. Let's say the operating system decides to protect a whole frame at given linear address. PRMEM would mark that entry for this frame in the page directory as read-only using the partial ROE primitive, and then it will mark the whole frame as read-only using the full ROE primitive. We will not have to be concerned with the EPT table because, as we just said, they're out of guest kernel control. This leaves one attack surface, the guest's own control register 3, which is the page table base address for the guest. An attacker who cannot override the protected entry in the page directory or the frame itself, or even flip the bits, might instead attempt to discard the whole page table and create his own new one. For this reason, CR3 would need to be heavily monitored, or much better be made read-only, or at the very least verified by the hypervisor. Intel virtualization technology provides a primitive for checking control register 3 and switch back to hypervisor mode once this register is flipped or changed, and hypervisor can do this kind of check. A slower solution but more secure solution is to prevent writing to the control register 3 and instead When switching processes, the page directory are just the new changes are added to the page directory in form of a diff, tree diffing. So we implemented memory ROE and PRMEM. PRMEM alone didn't show any kind of performance overhead because at the end it behaves as lightweight memory allocator, and even some parts of it are running at compile time. Reading from an RE protected memory didn't show any kind of overhead, whether it was partial protection or full protection for a page. The time took to read 10 gigabytes of data from normal pages and RE protected pages are almost exactly the same. However, attempted write operations show slight overhead. As for full ROE, write operations, even when they are slow, doesn't matter because they shouldn't happen at all. I mean, if they're happening, there must be an attack going on or someone trying to insert a rootkit. Same for the partial RE protected memory. The real slow thing here is the overhead imposed by writing to the same page frame that holds partial RE protected memory. Our first implementation showed almost a linear growth in the time taken as the number of the protected chunk increased. As a result, we implemented a faster lookup algorithms for ranges that took far less time, and it almost became constant time but slow. Thus, it's advised to avoid using partial ROE unless extremely necessary, as in the case for enforcing read only to only part of the page table but not the whole page table. Our work can be extended in many ways. First, write protection enforcement can be generalized to include both write and execution protection. One challenge to such protection is protecting just-in-time compilers, especially that the protection in its current implementation is irrevocable. Another big problem is having a fine-tuned hypervisor and operating system to have optimal division of labor while maintaining the smallest possible communication channel. For example, the current partial RE implementation can emulate up to one word at a time. By word, I mean channel width, whether it's 32 bits or 64 bits, but that can be improved by dispatching bigger buffers of data from hypervisor all at once. The difference here is that we will be saving switching from guest to hypervisor and from hypervisor to guest on every one word and reducing them to just two, like the operating system would dispatch a whole buffer of memory at once, and then the hypervisor would emulate the write operation at once and goes back to the operating system. We believe that the improvement in performance would be huge. To sum it up, we designed and implemented system that makes use of hypervisor to protect operating system from sophisticated attacks directed toward the kernel. Thank you.